All right, y'all. Today we're going to be talking about simplifying logarithmic expressions. It's kind of an extension of what we've been doing with exponentials, but now focusing on the log side of things. And I want you to remember from back when we talked in our graphing unit that we can switch freely between exponentials and logarithms by changing that base. But we haven't really talked about why that is, why we can do that. So let's look at number one. We have 2 to the x minus 1 is equal to 32. So this is currently an exponential function, and I want to convert it into a logarithmic function. And so I can do that by taking that inverse operation, by taking the log of the equation. But when I do something to one side, I have to do it to both sides. So I can rewrite this as log base 2 of 2 to the x minus 1 is equal to log base 2 of 32. So I've applied that logarithm. I have taken the logarithm of both sides of my equation. But what we're going to see is going to happen over on the left side, log base 2 and my exponential base 2. Those are the same bases. They are inverse operations of each other. So they are going to cancel out. While over on my right side, I don't have a base of 2. So it's going to remain log base 2 of 32. So I'm going to get this new function of x minus 1 is equal to log base 2 of 32. And now comparing my final answer back to my original, we can see that it's the exact same function. It's just it has been rewritten in terms of a logarithm as opposed to in terms of an exponential. So that's what we're actually doing when we make that switch between exponentials and logarithms. Now, that's a lot of work and a lot of writing that can feel kind of tedious. So we kind of shortcutted it. And we're going to do that shortcut here on number 2. So we have 4 to the negative 2 is equal to 1 over 16. And that shortcut we discovered is that when we convert from an exponential to a log, our base is just going to move from an exponential function to a log function on the other side of the equation. So here, my base of my exponential is 4. I'm going to take my base and I'm going to swing it on over to become the base of a logarithm on the other side of our equation. So this is going to become equal to log that base of 4 of 1 over 16. And then over on the side that I just moved my base from, my exponential is going to fall down and just become a normal number, negative 2. So that's kind of our shortcut. We call it the hook method, but it kind of cuts out all that extra writing because we know that this is going to be the eventual result anyways from taking that inverse operation. So we can just kind of shortcut it. Now, the key to be able to do this, notice my exponential is isolated. I have to have an exponent by itself to be able to actually do that hook method, to do that conversion. If we have other stuff going on with it, we got to move that stuff first before we can do that conversion from an exponential to a log. All right, go ahead and pause, y'all, and I want you to complete 3, 4, 5, and 6, just converting from exponentials to logarithms. You're not solving for x, you're just converting and then writing that converted answer. All right, y'all. So checking in, look through your answers for 3, 4, 5, and 6. Hopefully we're getting the same thing. And you can see when we're doing that hook method, it's really straightforward. We're just changing that base from a base of an exponential to a base of a logarithm, and that exponent is coming down. The important thing is I like to make sure I include the parentheses inside the logarithm and what's the base. And just kind of getting used to that idea of writing that base. We did a little bit of it with graphing, but we're really going to do lots and lots and lots of logarithms. So we want to get used to it. Okay. Now, our other thing that we're going to do is we want to also be able to convert from a logarithm back into an exponential. And it's the same idea and same concept, but just like we did before, let's talk about what's really happening. So if I want to convert from a logarithm to an exponential, then I'm going to take the basically exponential base of both sides. So I'm going to take a base of 8 and a base of 8. Over on the left side, my exponential base of 8 and my log base of 8, those are going to cancel out. Okay, over on the right side, my base of 8 is not going to cancel out because I just have that base of 8. So my new equation would be just 4 is equal to 8 to the 2/3 power. So when I take that base of both sides, because I'm doing that inverse operation, I should get it to cancel out on one side, and we end up with our nice converted function. Now, just like we do for converting exponentials, y'all, for converting logs, we can also do our hook method shortcut. So we have log of 0.001 is equal to -3. Now we know anytime we see a log like that, our base is 10, so we can hook that base of 10 to the other side, and this number is going to go up and become our exponent on that new base. So 0.001, too many zeros, is equal to 10 to the power of -3. All right, and it's really as straightforward as that, y'all. So go ahead and practice 9 through 12, converting these from logs to exponents. You can pause me and then unpause when you're ready to check your work. All right, y'all, and go ahead and check 9, 10, 11, and 12. Should be relatively straightforward. Remember, we're not solving, we're just converting. Okay. So now we've practiced going from exponents to logs and logs to exponents. We're going to do one last thing, though, and that's actually find inverse functions. And you might be thinking, Mr. Arbon, we've been finding inverses this whole time when we convert. And that is true, but we're more finding inverses of an equation as opposed to an inverse of an actual function. When we find an inverse of function, we have y equals x. That x is that independent, that y is that dependent. So this is something we could actually graph. And when we find an inverse function, instead of just switching it, we have to do something first, and that is that we actually switch our independent and dependent variable, our x and our y. So we're going to switch x and y first. So this becomes x equals 2 to the y plus 8 minus 3. And now that we've switched x and y, then we're going to do our conversion. But like I was saying earlier, right now our exponential is not by itself. It's got this minus 3 over with it. So I need to move that minus 3 first. So let's add 3 and add 3. So that would give me x plus 3 is equal to 2 to the y plus 8. Okay, and then from here, now my exponential is by itself, so now I can do my hook method and move my base over, my exponent down. So we get log base 2 of x plus 3 is equal to y plus 8. And then last but not least, I have converted it, but remember, I want to find the full inverse function. I don't just want to convert. So I'm going to subtract that 8 to get my y completely by itself. And that would give us the new inverse function of y is equal to log base 2 of x plus 3 and then minus 8. Okay, so same principles, same idea, but we're actually finding that full inverse of a function as opposed to more of just an equation. Okay. And we've done this before. We've talked about it before. You maybe even did a little bit on our review or our practice in Unit 5A, so this should be comfortable. So go ahead and do the same thing for 14, but this time we're starting with a log, and your final answer should be an exponential function. All right, and just like before, we want to start by switching that x and y. Then we have that minus 4 over with our logarithm. So first thing we want to do is add that 4 to both sides. So we get x plus 4. Then it is a log with no base, which means its base is 10. Moving that base to the other side, we get 10 raised to the power of x plus 4. And then last but not least, we have that 2. So I can divide that 2 over. And one thing that I see all the time is I see students say, Mr. Arbon, why didn't my base 10 become 5? Because I'm dividing by 2. Well, even though, yes, I have 10 to the x plus 4 divided by 2, that 10 is protected. It is a base. Okay, it's like it's inside a set of parentheses that are being taken to that exponent of x plus 4. So I cannot divide that 2 into that 10. Anytime I have something taken to an exponent, I would have to apply that exponent first before I could do any division. So you could write it like this, 10 to the x plus 4 divided by 2. But I like to put the 1/2 out front because then this looks more like a traditional exponential function that if we wanted to, we could graph, apply the vertical compression and the shift left by 4 if we wanted to. But just kind of a big misconception I want to make sure we're good on. We cannot divide into our bases. Okay, so we've kind of talked about that conversion piece. Now let's really talk about the simplifying piece, because we haven't really been making any of these simpler. We've more just been rewriting them. So we're going to focus on the simplifying side of things. But to do that, we needed to be able to rewrite, because we're going to kind of use a couple of different skills when we want to simplify. And that first one is going to come from really what a log actually is. Like when I'm telling you to evaluate a log, when I'm telling you we have a logarithm, what actually is that logarithm? And so our logs, we know that this number down here is the base. And you might not have been thinking about this, but when we take that base down, when we take that exponential away, this number that's left over, that was the exponent or our power. Okay, so even though we've converted something to a log, that number that's left over on the other side, it's still like the exponent or the power that it was before, which means this number on the inside was actually that base raised to that exponent. So we're going to call this our answer or our value. Okay, so when we're thinking about a logarithm, I want you to think about it in terms of this question, and that is the base to what exponent is equal to the answer. So that is the question that logarithms are really asking when we're trying to evaluate them by hand. So let's focus in on a log like number 17. We have log base 3 of 27. So let's think of that question. This base right here is my base, and I want to know what this base 3 to what exponent is equal to 27. So 3 to what exponent is equal to 27. And if we know our perfect squares, our perfect cubes in this case, we would know that 3 to the third is equal to 27. So log base 3 of 27 is equal to 3. So if I can answer that question, I can very quickly get to that value of my logarithm. Now, not all of our logs, A, are going to be this simple to simplify, or B, are going to be that easy to kind of think through. So I'm going to show you two other skills that we could use. And they're going to kind of involve our conversions that we just talked about, as well as our exponent properties that we talked about last class. So the first thing that we can do, let's say we're really having some trouble thinking of that exponent, and we can set this log equal to x. Okay, and so I'm really struggling thinking about it as a logarithm, so I'm going to shift it over to an exponential. So let's shift that base over, and we get 27 is equal to 3 to the x. Okay, so now we can more clearly see, hey, that 27 should be equal to 3 to some power. So what is that power? And so from there, we can more clearly see, oh, it should be 3. Or we could even rewrite 27 as 3 to the third. And once we've done that, well, if I write a better x, we can eliminate our bases of 3 and get 3 is equal to x. So we can find that same value that we would otherwise. Okay, another way that we could do this is instead of going through all that trouble of setting it equal to x, we could just right away think, well, I know 27 is equal to 3 cubed, so that would give me log base 3 of 3 to the third. And as we've been discussing, bases of logarithms and bases of exponentials cancel each other out. So those base log and base of my exponent of 3 would both cancel out and then just give me 3. Okay, so all three of these skills, whether you can think of that question in your head, whether you can set it equal to x and then maybe convert it over to an exponential, or whether you can just change the inside to have the same base and get it to cancel out, any of those skills are valid ways to try and simplify these logs. And as you start to do more and more of them, you're going to see, oh, I kind of am going to need to use all of these to simplify these logarithms. Okay, so I'm going to highlight a couple of these. If you notice, there are quite a few. I am not going to do all of these with you. I'm going to do probably about a third of them, and then I'll let you try some of the rest on your own. Okay, but let's focus in on a few. So let's look at one like number 15. So log base 4 of 32. So the question we're trying to find out is 4 to what power is equal to 32? And if we think of our 4s, 4 to the first is 4. 4 squared is 16. But then 4 cubed is 64. So our power is something in between 4 squared and 4 cubed. We know that because we have to make it into 32. But when we're dealing with non-whole number powers, I don't think our answer, that question kind of method, is going to be the best one for us here. So instead, let's set this equal to x and see if it can kind of help us out a little bit. So setting it equal to x, let's then convert it into an exponential. So we get 32 is equal to 4 to the x. Okay, and then this might look kind of familiar from what we did last class, our exponential equation. So let's rewrite 32 and 4 as bases of 2. So 32 would be equal to 2 to the 5th, and 4 would be equal to 2 squared. We still have that x on the outside, power to a power, so we can multiply. 2 to the 5th equals 2 to the 2x. Cancel out those 2's. We end up with 5 is equal to 2x. Divide by 2 on both sides, and we end up with x is equal to 5/2, or 2.5. And you might be thinking, well, Mr. Arbone, that really just looks like we did what we did last class. That's not something new. And that's absolutely true. And you'll notice as we shift between exponentials and logarithms through what we did on 5B.1 and 2 and what we're going to do on 5B.3 and 4 is you're going to kind of be shifting between logarithms and exponentials with some of these equations, depending on what's going to be the best for you to simplify that equation. So for us, this to me, I think, is the most effective method to simplify this equation. It's not necessarily the only way. There's a couple of other methods that you can employ, but I do think it's going to be the best one. Right? So we've done 15, we've done 17. I know you're going to Mr. Arbone, why are you skipping around so much? But let's look at one like number 19. We have log base 4 of the 5th root of 4. And something that we might notice right away is that 4 and 4 are already the same base. So that canceling out bases method is going to be really useful for us. But our issue is right now I have this 5th root in the way. So I got to get rid of that 5th root and make it into an exponent. Because if it's an exponent, then I can cancel out those bases. So the way that we can rewrite that 5th root, we talked about this 2 classes ago, is I can rewrite it as a 1/5 power. So log base 4 of 4 to the 1/5 power. Now that my 4 and my 4 are both there, I can cancel out those same bases, and my final answer would just be 1/5. So already 2 questions in, and we've applied 2 different methods to try and kind of simplify and figure this one out. Okay, let's look at another one. Let's look at a question like number 20. We have the natural log of e to the 10th over the natural log of e to the 5th. Okay, and this looks kind of crazy, but let's take it step by step. First thing we can see right away is we have these e's and we have our natural log. And if we remember, our natural log always has a base of e. Okay, now you might get that e confused with this e right here, but this is an exponential, e to the 10th and e to the 5th. So this base is the base of my logarithm and not my exponential. And so since the base of the log and the base of the exponential are the same, we can cancel them out. And that would simplify to 10 divided by 5. Now, I usually get 2 confusing things that happens. Well, one is we still think 10 and 5 are like an exponent, so we think we subtract them instead of divide them, which would be 10 minus 5 and give us 5. But they are no longer exponents. Once we've canceled out those logs and those exponential bases, this is just like any other number. So this is just 10/5. And 10 divided by 5 would be equal to 2. So once we cancel out those exponentials or those logs, y'all, this can really become a very simple and traditional question that we need to simplify, which can be really, really nice. Okay, let's do maybe one more, and then I'm going to let y'all kind of try a couple of these on your own. So let's look at one like 22. So we have log base 5 of 1. So we want to think 5 to what exponent would be equal to 1? And that might be weird to think about. You're like, well, I know multiples of 5s and I can do divided by 5s, but what makes it into 1? Well, there's a specific exponent that makes any base into 1, and that is an exponent of 0. So 5 to the 0 would be equal to 1. So that means log base 5 of 1 is equal to 0. And this is a nice general rule, y'all. Anytime you have a log of 1, no matter what the base is, it is always going to be equal to 0. So nice tool to have in your tool belt as you're thinking and simplifying and solving through these. Okay, y'all. So I did a few. I want you to go ahead and try the rest on your own. Do as many as you can. And when you feel like you've kind of exhausted your brain, you're at a stopping point, you can go ahead and unpause. I'll talk through the rest of these, okay? All right. All right, y'all. I'm going to kind of start at the top and talk through these kind of piece by piece. So let's look at 16. 16, we have log base 0.8 of 1. As we just discussed, log of 1 of any base is always equal to 0. So that one would be 0. Then we have 18. We have 7 raised to the power of log base 7 of 12. So this one's kind of a reverse, but it's a base 7 of an exponential and a base 7 of a logarithm. So those same bases are going to cancel us out and still give us just 12. Okay, moving on along, we have 21 log base 10 of 1,000. So we can just think about this one as 10 to what power would be equal to 1,000, and it would be 10 to the third. Okay, then 23. 23 is a bit of a doozy, but you just have to take them step by step, and that's kind of a theme for some of these. So I have log base 2 of 32 to the 100, which I already have an exponent in there. So you're like, what exponent to that exponent? I don't even know, but let's think of how can I rewrite 32 as a base of 2? And 32 is equal to 2 to the 5th. So once I have 2 to the 5th to the 100, I can multiply that power to a power to make it 2 to the 500. And those bases of 2's will cancel out. So 2 and 2 cancel out, and we're left with just that exponent of 500. Okay. Then 24, we have the natural log of the square root of e. This one's pretty straightforward. Rewrite that square root as a 1/2. Those bases of e's will cancel out, and we do end up with 1/2. On 25, we have log base 4 of 64. Well, 4 to what power is equal to 64? 4 to the third power. So we get an x value of 3. And then log base 5 of 1 over 125. Some of y'all, this might have really thrown you for a loop, but don't forget that fraction. Anytime you see a fraction, you know it is a negative exponent. So 5 to the third is equal to 125, which means 5 to the negative third is equal to 1 over 125. And then looking across our bottom row, y'all, we have 27 for natural log of e to the 6th. Well, once again, natural log has a base of e, so those bases cancel out, and we get 4 times 6 is equal to 24. Now, a common misconception I get on 27, y'all, is thinking that this 6 that's an exponent is still an exponent, and so this would be equal to 4 to the 6th as opposed to 4 times 6. So don't forget that when that e's cancel out, that 6 comes down, or really it's any exponent comes down, and it's treated as a normal number as opposed to still being an exponent. Okay. Then 28, very similar to 18, we have a 6 raised to the power of log base 6 of 18. That base 6 of an exponent, base 6 of a log cancel out, so we have just 18. And then last but not least, we have 5 log base 5 of the 5th root of 5, which is quite a mouthful. But once again, take it piece by piece, switching this 5th root to a 1/5. Our log base 5 and base 5 of the exponent cancel out. We get 5 times 1/5, which would then simplify to just 1. Now, we've done quite a few of these. But as you can imagine, you could keep doing simplification of logs through all sorts of numbers and all sorts of variables all throughout. So the better you're going to get at this with more and more practice. So our activity today at I Have Who Has is a whole bunch of simplifying log practice. And so the more and more you think about these, you're going to start thinking some of these really quickly. Like, oh yeah, fraction of negative exponent. Oh yeah, radical fractional exponent. Oh yes, power to a power. Or, oh, set this one equal to x. You're going to kind of start to get a little better at these and thinking through them as you do them more and more. So it's just going to kind of take some practice. Okay, the very last thing, like we did before when we were doing our conversion, we talked about, okay, how does this apply to functions? Well, we're also going to talk about how does this simplifying of logarithms really apply to functions, something we're actually going to use them for. Because really you're like, well, Mr. Bone, how often am I going to have to know what 4 natural log of e to the 6 is? Well, you might have to know it if you have an actual function, you're trying to evaluate it, and that's part of your evaluation. So we have something like 30, f of x is equal to log base 4 of 61 plus x. And we want to know what's the value when x is equal to 3. So this seems almost kind of crazy, but really all we're doing is we're plugging in that value of 3. So f of 3 would be equal to log base 4 of 61 plus 3. Okay? And when we plug in that 3, we can then just simplify and reduce from there. So 61 plus 3 is equal to 64. So log base 4 of 64. And now, just like we did up above, we want to think, okay, 4 to what power would be equal to 64? And that would be 3. So our f of 3 is equal to 3. So now we're really kind of applying those simplifying log skills as opposed to really what we're doing above. It's more of like practicing those simplifying log skills so that we can actually use them for applicable log functions like this. Okay, let's do one more together. Let's look at 32. We have g of x is equal to log of 100 divided by x. And we want to know what it is when x is equal to 10. So g of 10 would be equal to log, and I'm going to go ahead and add in our base 10 because I think it's going to be helpful, of 100 divided by 10. So that would simplify down to 100 divided by 10 is 10, so log base 10 of 10. Okay, and we already have the same bases, but we don't have an exponent, so I'm going to add in 10 to the first because anything that's just itself is just itself to the first power. So now we can see those bases of 10 and 10 cancel out, and we end up with just g of 10 equals 1. All right, y'all, that really is all there is to it. I want you to go ahead and try 31, 33, and 34. One of these has an answer that's probably going to stump you a little bit. So just know one of them you might get kind of stuck when you get to the end, but I want you to think through it and see if you can figure it out before I reveal it here in a minute. So go ahead and pause and try 31, 33, and 34. All right, and let's start off with talking about 34. So 34, we have e to the natural log of x minus 4 when x is equal to negative 3. So plugging that in, negative 3 minus 4, we get negative 7. And then we have e to the natural log base e of negative 7. Those bases are going to cancel out, and we get just negative 7 as our value. Okay, then moving on up to 31. 31 was our stumper. We plug in that 7. 7 minus 7 is equal to 0. And so we have log base 5 of 0. And we think, can I take the log of 0? Is 5 to some exponent going to be equal to 0? And the answer to that is no. There's no way that we can take a base to an exponent and make it equal to 0. That's why our exponential functions have that horizontal asymptote at y equals 0. We can't have any 0 values out from an exponent, and we can't have any negative values. So if you try on your calculator, if you're trying to kind of test this or check this out, you'll see if you try to do the log of 0 or the log of a negative number, it will tell you error not in the domain because we don't have those numbers in our domain and we can't actually evaluate them. So that's why 31 is no solution. Okay, we don't actually have any value when x is equal to 7. Okay, last but not least, on 33, we have 4 log base 3 of 3x plus 42 divided by 4, and we want to evaluate this one when it's equal to negative 2. And this one, it's just kind of a step-by-step, plugging in and simplifying piece by piece. We do eventually get to 4 log base 3 of 9, which we can write 9 as 3 squared, cancel out those bases of 3. We have 4 times 2, not 4 squared, because that 2 comes down and multiplies. which then, of course, gives us 8. All right, y'all. And that's really all there is to simplifying logarithms. We're going to expand this into actually solving logarithmic equations, which you might kind of feel like we've almost already done already, but we're not really solving quite yet. But we're going to expand that a little bit more next class. But for now, go ahead and practice with our I have who has activity and the practice.